Hey, it's not going to be so bad.
Fine.
8. Well, the good thing about 18.1 is, even though it's titled Graphing Polynomial Functions, you're doing sketches. You're not graphing super detailed, and you actually won't need graph paper. So the graphs I sketch up here are going to be good enough for what you need for this lesson. So it will be a graph. It'll be a not super detailed graph. There's specific things you need in it. Let's just get started. You will be able to do the entire first question or first page on your own. I'm going to have you do that once I read it, and then I'm going to have you check it with somebody next to you. Number 1, each graph below shows a polynomial of the form blank. That's confusing looking. We've looked at it once before briefly. That's how you write a polynomial in a generic form. As soon as I put a number in there, it becomes a specific problem. And I don't want to say this polynomial. I want to say for every polynomial possible. And there's not a good way to do that except for what they've come up with here. This is kind of how you represent a polynomial. You don't have to fully understand it. Just look over it and understand that that is how any polynomial could be written. Apply what you know about graphs of polynomials to match each graph to one of the equations below. Write the equation under the graph. You don't have to write the full equation. Let's do this. Let's number each of these. Those look kind of complicated. All you're doing is matching. You don't have to know how to graph the entire thing on your own. You have to know how to match the equations to the graphs. That's what you're doing right now. Without a calculator, go ahead and see how many of those you think you can match up. Raise your hand if you're done matching. I can give you a little bit more time.
I think I'm either having a brain fart or I can't remember anything I've ever in the past 16 years of my life. I don't know why.
I'm going to pair you up. If you're done, talk about your answers. If you're not done, you weren't sure about one, see if your partner has that, and you guys can discuss it together. So just the people you're next to. So you two share, you two share, you three share, you two. Share your answers or talk about what you did not get.
Or 1, 3, 5, 4, 6.
Oh my goodness.
I just don't. I don't remember like what in this problem was going to tell me what. I had 2, 3, 6. I know like the negative and like but I just can't. I know it means like I think there's this negative. Yeah.
You know these are the cues are
So what?
put, right?
Now.
If that is cues, you know it's one of these cues.
Down here.
Now, what can you tell me that is there's 1 second to that, the rest of it.
Like if it had like a 2, an extra 2, then it would be like
Either one of those. Yeah.
no, it's negative. The negative.
You guys have all the same?
Less than the degree.
Yes.
By 1.
Oh, I see what
But what else
That's
is
what I
true?
did. Why I did
There's
that.
three points at the same time.
No.
So those 3 points at the same time mean that's the third degree function.
Yeah.
So like,
No.
yeah. I didn't think we got one correct.
Like,
Well,
draw a line. Yeah.
And then we did that thing where it's like we count the little bump things, and then it's like minus the bump and then extrema.
Now this one,
Oh.
it doesn't have to be,
You explained it to him?
but
I don't know if I
what
did it
degree would
right.
it be based on the arcs too?
There's 3 is an extra, it means you only have 2 bumps. 1, 2. So now we got one of these.
I didn't know that. I just feel like, okay, a lot of numbers, that means a lot of
And then
space.
add 1. Yeah.
It's cheating.
All right, finish up your discussion.
There is cheating.
All right, let me go over these.
Not the exact numbers. Just-
For every graph here, I should say for every equation, you only need to know the first term because the degree will tell you a lot and the coefficient will tell you something. So I have only 2 of them that are x to the 4th or even. The other ones are x to the 3rd, x to the 5th. If it's even, what will happen is they will have the same end behavior. It will go the same direction at both ends. How do I know if it does this first one or this second one? If it's positive, it will do this, just like your x squared graph. We all are good with x squared, right? You know, it's a parabola shaped up. So that tells you if I have an even power and a positive coefficient, it will do that. Then if I have a negative coefficient, it's going to do the opposite. So the only 2 that are even graphs are these 2. This one, E, is your positive coefficient, like that. I know it's x to the 4th, but it's even with a positive coefficient. So that would be letter what? Number what? Yep, and so this would have to be 3. Now, we have some odd ones. So if I have this graph, that could be an x cubed function, or there is a way that it could be an x to the 5th function. However, this could not be, I'll do that again. This could not be an x cubed function. If you look at the degree and subtract 1, that is the most amount of humps, as Thomas calls it, or bumps, as Jillian calls it. The mathematical term is extrema. Think of extremes. Minimum, maximum, those are extremes. So this one has 2 maximums, 2 minimums. That's a total of 4 extreme points. This is very extreme, but we don't count that because infinity is not a number. So if I have an x to the 5th power, I can have -1. I can have at most 4 extrema. Do we see why this can't be x cubed? You can only have, subtract 1, 2 extreme or mins and maxes. So that tells me that I look at my graph. That tells me that both of these have to be the x to the 5ths. And both of these have to be x to the 3rds. Now we just have to figure out the end behavior, which way it's going. Think of the easiest function you can come up with. Our easiest even one is x squared, and you know what that looks like. Our easiest odd ones could be this or this. Those are ones we should know how to graph. This you should know looks like this. Look at the end behavior. Down, then up. This graph has the same end behavior. So if this is positive, the end behavior will be down, up. Negative infinity. As I go to infinity, it goes to positive infinity. So this is a positive leading coefficient. This one had a negative leading coefficient. Match them up that way. This one, it's starting down, ending up. Positive leading coefficient, negative leading coefficient. Any questions on that? I didn't actually tell you all the answers, but hopefully I gave you enough to figure them out. I would never expect you to graph this without a calculator and get the graph that's on there. I just want you to be able to know a little bit about what that graph looks like, enough to match it up. All right, turn the page. We will only have time today to do questions to C, D, and E. There's not a lot of space there, so that's what we're doing. C, D, and E, so you can write them on separate paper or in your book. Yes. What is it? Do you need graph paper? No. No graphing calculator. Before we get on that page, if you look at 279, you'll see that highlighted phrase I've been using, relative extrema. It says in that last sentence with the highlighted word, they also have at most n-1 relative extrema. N is the degree. So if I have a degree 10, it can have 9 humps or bumps or extrema mins and maxes together. So it cannot have 9 mins and 9 maxes. It can have 9 total mins and maxes. All right, let's look at the top of 278. Polynomials can be written in factored form or in standard form. You guys are familiar with both. Anytime I say factor, it was probably started in standard form, and then you turn it into a multiplication or a factor. Each form provides useful clues about how the graph will behave. Question 2. Sketch a graph of each function. For graphs B through E, identify the information revealed by the factored polynomial compared to the unfactored compared to the factored. We'll pretty much do all these together. So starting with C, our graph will be last. We are going to identify the information revealed by the unfactored polynomial. I'm going to call it standard form. So write down under part C, or wherever you're writing it, standard form. This is the function in standard form, and just by looking at that without a calculator, there are going to be at least 3 things we should know. Give me one.
2 extremes.
Oh, that's a 4th one. Yes, add that. Go ahead. That's not one of the things I will make you do, but I'll check your graph. So at most 2 extrema. Very good. We didn't talk about that last hour, but I guess we did once we got the graph done. Very good. What else?
It's gonna be going up to the right and down to the left.
Up to the right, down to the left. When we first learned end behavior, I had you write it very specifically in arrow notation. Not requiring that you write it and then state how you know. I'm guessing that was because it was odd degree. Odd degree tells me it's going different directions. And how do I know where to start? Because it was a positive leading coefficient. I'm not sure if the abbreviation has 1 F or 2. I think coefficient is abbreviated with 2. Anybody have another thing that you know based off of the function?
It's y-intercept is -9.
That's exactly what I wanted. Y-intercept, -9. It's always going to be your constant term for this reason. For y-intercepts, x is 0. If I plug a 0 in, a 0 in, a 0 in for x, I'm always going to get the constant term. The other thing I want you to notice is something that we haven't talked about in a while. So put some kind of mark where you're at and turn to page, let's see if I can find it again, 230. 237. Page 237. You'll see two highlighted words. Page 237. The highlighted words are even function, odd function. I have odd degree. This 3 makes it odd degree. That doesn't necessarily mean it's an odd function. So let's read at the bottom of 237. The last paragraph. The function blank is an odd function. Notice that every power of x is odd. Is that true for our problem? Is every power odd? 3 is odd, 2 is not odd. So even though it's an odd degree, 3 is odd degree, it's not an odd function. So let's look at what it says in the last sentence. Symmetry about the origin is an attribute of all odd functions. If it were odd, my graph would have symmetry about the origin. We probably need to write some of that down in today's notes or just refer to page 237. Go back to today's notes, put page 237 or write down odd function. All degrees are odd. All exponents, I should say, are odd. Symmetry about the origin. Odd function. Every exponent is odd. If that happens, symmetry about the origin. Let's flip back again so we can learn about the even functions again. So back on page 237, I'll read the paragraph above that. The function blank is called an even function. Notice that every power of x is even. The last sentence there says symmetry over the y-axis is an attribute of all even functions. So let's add that to today's notes. Even functions, symmetry about the y-axis. So the last thing I'm going to write under standard form is symmetry. Does it have symmetry about the origin or y-axis? No, because it's neither all even degrees or all odd powers, I should say. So I'm going to write under symmetry, no, none about y-axis or origin because it is not even or odd function. Luckily, factored form is only going to have one thing. Standard form has 3 to 4 things. End behavior is probably the most important. But we should be able to tell how many extrema, the y-intercept, and if it has either of those symmetries. Let's write down factored form. Sure, you could have probably said the end behavior from this factored form. You could see it's going to be x cubed, and it is going to be a positive x cubed, but it's not quite as easy as the standard form. Anyone have an idea what factored form reveals? It's kind of important for our graph. Yes.
Solutions.
Solutions, which we also call zeros, which we also call ding, ding, ding. X-intercepts tells me something about my graph. X-intercepts is what I would call them here instead of solutions, but they are the same thing. I'm going to write, I know the x-intercepts, and they are -3, 3 and -1. Now we're going to graph just this information. So your graph can be a very rough sketch. You don't need graph paper. Just a simple X, Y axis. I'm going to graph this first. I'm going to graph my x-intercepts. Then I like to graph my y-intercept. Then I'm going to graph my end behavior. So I know it's going to start down. I kind of just put the arrows in the graph at the farthest ends. The other two I don't graph. Just make sure you note, hey, it shouldn't be symmetrical, and it should have at most 2 extrema. So connect those. Some students have a hard time connecting these. They're all a little different. So you know this starts down, so it's going to have to touch this x-intercept. So have it go through that point and come back to that one. I don't care how high it goes. It could go way up there, or it could go just there. Doesn't matter as long as it goes through both of those x-intercepts. Going to have to come hit this and through that one. That has 2 extrema. You don't have to plot those. And it's not symmetrical. Those are the kind of graphs we're doing today. You're writing this out, and you're plotting just those things. Questions? All right, let's get to D. We're listing out the things we know based off the standard form. Should be easy now because we've already done 1. Go ahead and see how many you can get.
Not bad.
So I have at most 3 extremes, always the n, the degree minus 1. The y-intercept is the constant term. What if this constant term wasn't here? What would be the y-intercept? 0. End behavior is based off of 2 things. The degree, 4 is even, and the fact that it's a positive x to the 4. Symmetry. I want to know, is every power odd or every power even? In this case, 4 is even, 2 is even. This is considered x to the 0, which they say is even. So this is not only an even degree, it's an even function. And if it is, we just took notes on, it will have symmetry about the y-axis. So when we make our graph, the y-axis should be like a mirror. It should be symmetrical. And let's do factored form. That tells me my x-intercepts. -3, 3, -1, and 1. All right, let's make our sketch. I know you can all plot x-intercepts and y-intercepts. The end behavior, again, I just put the arrow at the farthest end of my graph, and I'll connect it when I'm done. As I connect these, I want to make it symmetrical. So I'm going to need to come down and go through this first point, back up to this point. As soon as I hit the y-axis, I need to make it symmetrical, make it look exactly the same. If yours came down farther, then this one needs to come down farther. How are we doing with connecting the dots? For some, it's like, I don't get what you don't get, and some are like, I don't know how to connect them. Wyatt? Good. All right, do we need more time for the last one? All right, go ahead and get started on that one. Oh, did you guys check your extrema? I forgot to say that. Check and make sure the extrema work. I think it did. I would hold off on connecting your points for this one. Let's check it at most 4 extrema. End behavior. I know that because it's odd degree 5 is odd, but it's a positive x coefficient. Y-intercept 0. Symmetry. There is no symmetry about the y-axis or origin because it's neither even nor odd function. I don't know if there are other symmetries out there. That's why I don't just say no symmetry, because maybe there's a symmetry I don't know about or haven't studied yet. that it might have. But as far as I know, there's no symmetry about the y-axis or the origin. Factored form tells me my x-intercepts, 0, -2, and -3. And I put a star by them because this is really what we call a repeated root. It's times itself. It's happening twice. And that affects the graph. We haven't graphed these before. They're actually easy. I just need to tell you what it means. So let's together plot our x-intercepts. We have 0, -2. I'm actually going to put a star there. And -3. Probably good to erase the star when we're done, but I wouldn't take off if it was there. The star tells me something different is happening because I have a special type of root. It's repeated. So I've got those plotted. I've got my y-intercept already because it already happens to be 0. End behavior going to end going down, going up. Anybody want to guess what happens with the graph with the repeated special root? Ooh, it makes a circle. Good guess.
Like it just
Your
goes
guess is
around,
better than everybody else's because nobody else has guessed.
It goes around and it hits it, and then it goes around and it hits it again.
No? What do you think?
It's like a parabola where it just goes up, it hits the point, it doesn't cross.
Right. It doesn't go through the point. Before, when we had graphs, if I had these points, it would go through that one and through that one and through that one. These bounce. So if this was a special one, it would not go through. It's like a shatterproof wall. It would touch it and bounce right back the way it came. It would not go through the point. It would touch the point and bounce back the way it came. So let's start. We have this end go up to that special root. It's going to bounce back down. Because it's repeated, there's 2 of them. So it's going to bounce back down. I have to get it to go back up. It's going to bounce back down from that one also. This one is not special. It's going through it. Try not to make these, make curved lines. This is not my best work right here. Better. Check your extrema. I have 1, 2, 3, 4 extrema.
Oh my gosh. Ian, you're so right. And then things like bounce off the shield.
Wow. You know, Captain America has a
Right.
shield and then it bounces off.
There you go.
I would like a circle like better.
Analogies are insane.
That your graph cannot go up, circle. I don't know if I could ever. I don't think that could be a single graph. I think that would have to be a graph, and then I could just graph circles. Let me put your homework up to get started.
No, it would, I don't know what the equation would be.
I don't even know what you're talking
But like you would draw the graph and then it would.
Yeah.